What's going on, guys? Today let's talk about the scalar Klein-Gordon quantum field. But before we do that, I want to talk about something new that's coming out on my Patreon page. So if you become a member to my Patreon page, then you'll be able to receive quite a bit of content that's going to be coming out as time progresses. One of these pieces of content are early access videos. Some of them are already out on my Patreon page on statistical mechanics. The next tier up, you'll be able to also not just get early access, but you'll be able to now get notes from me. And so these are kind of just a taste of what these notes look like. So we have here Klein-Gordon Lagrangian notes that I've made. And these are actually pretty well, I think, made. It took me a while to make these notes, but you can see it's really sort of beautifully done. We have our Klein-Gordon Lagrangian. That's the name of this particular note, and we could see. I try to sort of follow the content all the way through. I number equations that I think are necessary, and I also provide some illustrations to help us conceptualize what might be going on here. And I have some explanations to these notes, and I also have more illustrations, as you can see, right? And then what's particularly nice about these notes is that you can make your own notes here on the side. So I've in some of these notes so you can follow along here. You can look at each step and you can write in the margins whatever you want. You can watch my videos and write your own notes in the margins as well, right? So this is all going to be offered on my Patreon page, and this is the first piece of note that's going to be offered there. So you can go to my Patreon page. Again, you can sign up to get early access, or you can sign up to get early access and exclusive content, exclusive member content. And these kind of notes are going to be under that exclusive content. Let's get into the material now. So we want to recall a couple of things first. We want to recall that we have a Klein-Gordon Lagrangian that we've talked about in the past. We also want to recall that we have developed a way to understand what our conjugate field is, right? So our conjugate field looks like this. And we also have developed the solution to the Klein-Gordon equation, right? So the Klein-Gordon equation is the equation of motion that came out of the Klein-Gordon Lagrangian, right? So that's stuff we all did in the past. Let's get into, now that we have those sort of fresh in our mind, let's get into developing the conjugate field for the Klein-Gordon Lagrangian, right? So remember, we have the solution. Now we want to find the conjugate to that solution. This is almost like complex conjugation, if you will, when we're talking about, say, complex numbers. But it's not really that process. This is a different process, but we're calculating a field that is conjugate to the solution that sort of comes from the Lagrangian, right? So we want to keep this all fresh in our minds. So let's talk about this here. So here's our Lagrangian again. We're taking the derivative again here with respect to the derivatives, specifically the time derivatives. So that's this right here. Now this here we could think of as this squared, right? Because it's the same value. And then we have this here and this here, and the reason they're canceled out is because in this particular case we're taking the time derivative, right? We don't have to, but this is just an example where I'm taking the time derivative, and from that we can see that the only time derivatives show up here. So the derivative of something squared is basically you bring the 2 over, and that's going to cancel out with this 1/2, and what we get is this, right? So this is the prescription by which we will find out what the conjugate field looks like. Now, we literally take our solution right here and we plug in to here, right? So here's our solution, so here's our solution, right? And we can think now that we want to really just take the derivative, right? So we find where these derivatives are. So right, they're in the exponents. We're taking the derivative with respect to the time component of these four vectors. And so these are both four vectors. If we're taking the derivative of just the time component, we're taking out the 0th component, right? We take out the 0th component here, then we bring the i's outward, and we swap out for a negative, right? Because we have this negative here, and we get this here for our conjugate field, right? So I've written here, I'll erase this just to reduce clutter, but this is a field, right? It's a function of space and time. The reason I shouldn't really have taken that out, but we can condense it down to look something like that, right? This nomenclature is sort of reminiscent of a four vector. It encapsulates time and space. And that just, and I've rewritten that again right here, right, where this is a function of time and space, and this here is a function of time and space. And then we also have the derivative, right? So that's what we had up here. So this is really just a reiteration of this, just a little bit more explicitly drawn out, showing that these are indeed four vectors and we're taking derivatives with respect to their time components, right? So we haven't gone quantum yet. In order to go quantum, we need to now apply the Heisenberg uncertainty principle. And I'm going to talk a little bit about that here because I think this is something that is often overlooked. This was here because I recorded, but for some reason the recording didn't happen. So I'm going to explain it again here. But so in order to go quantum, we need to apply the Heisenberg uncertainty principle because we've still been talking about just classical fields. So in order to go quantum, we need to be able to understand that the conjugate, we cannot simultaneously understand the value of the conjugate field and the solution to the Klein-Gordon equation. Recalling again that the Klein-Gordon equation came from the Klein-Gordon Lagrangian, right? So we have a solution and a conjugate to that solution. And in order to apply Heisenberg uncertainty principle, we have to understand that the conjugate, we can't simultaneously know the value of the field, the value of the conjugate field, and the value of the solution at the same point in time. So I'm going to draw this out. This is also fleshed out in my notes that I'm providing on Patreon. But we have a field, say, okay? And I'm going to call this our conjugate field. And we have another field, say, that looks like this. And I'm going to call that our solution. Okay? Now, let's take a look here and say we're interested in this spot right here. The idea here is that we're postulating a relationship here, right? So this is the relationship, and this is a version somewhat of the Heisenberg uncertainty principle. Let's recall what a commutation relationship is. A commutation relationship is basically if two things commute with one another, i.e. in basic algebra, everything commutes with one another. If two things commute with one another, then the fundamental idea in quantum mechanics is that if they commute with each other, then you can measure their observables, right? You can measure them simultaneously. If they don't commute with one another, then you can't. So if you recall back from your quantum mechanic beginnings, and what we've talked about this before, is that you can't measure position and momentum simultaneously, okay? And what came from that was that we had operators that were associated with position and momentum, and when we took the commutation relationship between those two, then we found out that that commutation relationship did not equal 0. In other words, they did not commute. So things that do not commute, right, are things that you cannot measure simultaneously. And so when we see these two things that don't commute, because this is not 0, this sort of begs the question, how can we understand this? And the way I like to understand this is that at a point, you cannot measure the value of both fields at that point. You can only measure a value of 1 at that point. But if we're to measure 2 points, right, this is where we have, say, x and y, and they have to be 4 vectors, right? So that's reminiscent right here, x and y, then we can measure them, right? Because if we remember here, this guy here's the Kronecker delta. Kronecker delta looks a little something like this. We have 2 points equals 0 or infinity if x equals y, or if x doesn't equal y. Right, so this is 2 separate points, right? So at 2 separate points, then they commute and we can measure the values of the fields. Okay, at 1 point we cannot measure the value of both fields. That's the idea. So at 1 point you cannot measure, at 2 points you can. And that is essentially the Heisenberg uncertainty principle. You can measure, say, position here, but if you measure position here, you cannot measure momentum there, and vice versa. But if you measure position here, you can measure momentum here, right? That's the idea. Now to get from this here to this here, we need all the ingredients we've talked about so far in this video. And from those ingredients, we can then formulate this relationship right here. We have another commutation relationship that basically says you cannot create, we have a creation operator and an annihilation operator. You cannot create and annihilate operators you cannot create or annihilate particles that have the same momentum, but you can do it to particles that have, you can do it to particles that have different momentum, right? So that's the idea here. Okay. And this is the result from this analysis on Klein-Gordon, on the Klein-Gordon-Lagrangian. So again, if you like this kind of content, you can subscribe to my YouTube page, you can visit my Patreon page, and if you're oh so generous on this Christmas holiday season and you're interested in this kind of content, you can go and you can subscribe on my Patreon page as well, if that's something, if this is the kind of content that you're interested in. So with that being said, I will see you guys in the next one.